Hi guys, welcome to my lesson on medians and altitudes in triangles. This lesson goes hand in hand with our last lesson on perpendicular bisectors and angle bisectors. Because just like those types of lines, if you draw all three of these, medians and altitudes, in a triangle, they will also converge at the same point. There's a point of concurrency associated with medians and altitudes in triangles, just like we learned with perpendicular bisectors and angle bisectors. So we're going to work with medians and altitudes here. Before we do that, we probably ought to define some new vocabulary. What is a median? We draw a median in a triangle. Okay. What we do is we draw a line segment from a vertex, if we call this triangle ABC. A median could be drawn from A to the midpoint of BC. So if I picked the midpoint, and I would know it was the midpoint if it was marked as such. If I connected a vertex to the midpoint of the opposite side, that would be a median. Okay, now it just so happens that if I did this for all three sides in a triangle, I'm going to pick the midpoint of AC and draw another median. And I'm going to pick the midpoint of AB, and we're going to draw another median. That's about the midpoint there. All three of the medians, if you draw them in a triangle, will converge at the same point. And this point is called the centroid. Okay. And what's cool about the centroid is it represents the center of mass. Okay. Center of mass of a triangular shape. Okay, so if you were trying to make a triangle that you wanted to balance, then you'd be looking to find the centroid. If you want to find the centroid, draw three medians, and they will all converge at that point. Okay, now we have another type of line here called an altitude. If I were to draw another triangle, let's call this DEF. An altitude is something you've been working with for a while, although you might have called it by something different. You might have called it the height. Okay, height. Or altitude. Altitude. Okay? If we draw a line segment from a vertex in a triangle to the opposite side at a right angle, then we've drawn an altitude. And yes, you can draw three altitudes in a triangle and they will converge at the same point. And that point we call the orthocenter. So here I'm going to try to draw this guy at a right angle to the opposite side. And this guy I'm going to try to draw at a right angle to the opposite side. And if I do that, they'll converge right there at the orthocenter. Okay. All right, let's take a closer look at medians and centroid. Okay, so now that we know what medians and centroid are, let's take a look at our centroid theorem. There's one more interesting thing about centroid that I didn't mention. Not only is it the center of mass for a triangular shape, but it also happens that when you draw a median, such as median AK here, that this centroid happens exactly 2/3 of the length along the median. So if I took the length of AK and I multiplied it by 2/3, I would have the length of AP. And likewise, if I knew the length of BL and I multiplied it by 2/3, I would have BP. So the centroid occurs 2/3 of the length along the median from the vertex from which it is drawn. Likewise here, if I know the length of CJ, then CP will be 2/3 of the length of CJ. Another way to look at it is that the ratio of these segments 2 to 1. It will always be 2 to 1 if you want to look at the individual segments rather than the entire median. This segment is 2/3 of the whole total median. Well, that means that PK must be 1/3, right? So their ratio will always be in the ratio 2 to 1. That's a good quick shortcut that you can use. Let's try a couple of problems here with centroid. Okay, in triangle XYZ, P is the centroid and YV equals 12. They want us to find YP and PV. Okay, so they want us to find these guys, YP and PV. Okay, P is the centroid, YV. So this whole length equals 12. So I know YP is going to equal 2/3 of YV, or 2/3 times 12, right? So that's going to be 24/3, which is 8. Okay, and then if this is 8, well, I can just subtract now to get PV. So PV would be 4. Okay, and notice, again, YP is 2/3 of the length of YV. And you can look quickly at these two segments and see they're in the ratio of 2 to 1 to each other. This segment will always be twice the length of that segment. In this problem, we have triangle LNP. They're telling us R is the centroid, and LO is 30 units long. Okay, so I'm just going to mark this entire median here is 30 units long. Okay, and they want us to find LR and RO. Okay, so how long is LR and RO? This is going to be 2/3 of the length of the whole median. 2/3 times 30 is going to be 60/3, or 20. And this must be 1/3 of 30, or the remaining 10. We can say 30 minus 20 is 10. We can also quickly recognize that this segment is half the length of this segment because of that 2 to 1 ratio we talked about. Okay, here we have triangle ABC. They're telling us that CG is 4 units long, and they want us to find GE. Okay, well, again, these segments are going to be 2 to 1. So if this segment is twice as long as that segment, well, the segment's just going to be 2. And notice that makes the whole median, CE, 6 units long. And in fact, CG is 2/3 of that whole median. 4 is 2/3 of 6. Here we have triangle JLN, and JP, they're telling us, is 16. So this is 16 units long. How long is PM? Okay, just like the last problem. If these segments are in the ratio of 2 to 1, this segment's half as long as this segment. So it's going to be 8. Okay, total length as a median, JM, is 24. And indeed, JP equals 2/3 of that 24. Okay, JP equals 16. Excellent. All right, let's see if we can try a problem where we can apply this idea of centroid. An artist is designing a sculpture that balances a triangle on top of a pole. In the artist's design on the coordinate plane, the vertices are located at 1, 4, 3, 0, and 3, 8. What are the coordinates of the point where the artist should place the pole under the triangle so that it will balance? So hopefully you recognize that this point we're looking for is the center of mass, which we call the centroid. Okay, so in order to find this, I think we're going to have to plot these points. Why don't we call these points A, B, and C? And we'll just get them on the coordinate plane. A is at 1, 4. Okay. A is at 1, 4. Good. B is at 3, 0. So B down here at 3, 0. And C is at 3, 8. So that's going to be up here. Okay, that's a nice looking triangle. Let's just connect those endpoints. And how are we going to find the centroid? What types of lines do we have to draw to converge at the centroid in a triangle? We're going to have to draw medians. And how do we draw medians? We're going to go from a vertex to the midpoint of the opposite side. Now, one of these medians in this triangle is fairly easy to draw. The two others are, it can be done, but one's super easy. Which is the easy one? Well, you might notice that BC is a vertical line, and so it'd be easier to find the midpoint of BC than the other two sides. It's a vertical line that's 8 units long. So if I go up 4 units, I'll be at, let's call this point E. Okay, and this has coordinates of 3, 4. Okay, so I can draw a median right there. There's one median. It's just going to be a horizontal line from A to E. That guy's not too bad. Okay, well, we only have to draw one of the other two medians because we know all three of them are going to converge at this point of concurrency. So why don't we draw the median from B to AC? Let's find the midpoint of AC. On more complicated ones, you can go ahead, let's call it point D. Okay. You can calculate D using your midpoint formula. Remember, x1 plus x2 over 2, comma, y1 plus y2 over 2. You say 1 plus 3 over 2, comma, 4 plus 8 over 2 to get the y coordinate. And that would clean up nicely to 4 over 2 is 2, and 4 plus 8 is 12, divided by 2 is 6. Okay, so if I go over 2 and up 6, yep, indeed, I do arrive at that point that I graphically plotted for D2, comma 6. Okay, so let's go ahead and draw this median. And you can see it's going to look something like this. Okay. And there's our centroid. Since we've already used C, I won't use C for centroid. Let's call it I for intersection, I guess. What are the coordinates of point I going to be? Okay. Now, on some more complicated problems, what you're going to do is you're going to come up with an equation for each of these medians and then set them equal to one another to find out where they intersect, where they have equal value, right? And one of these lines, one of these medians is easy. This is y equals 4. That's the equation for AE. What about BD? BD is not quite so easy. We could calculate the slope and then put it into point slope form and work on it. It's a good way to do it, actually. But on a problem like this, there's a shortcut. Does anybody see what the shortcut is? Using some other property of medians and centroid that we learned about. Well, I've got this median AE, and I know that AI is going to be 2/3 of AE. So let's use that to figure out AI. AI is going to equal 2/3 times AE. AE is 2 units, right? I go from x equals 1 to x equals 3. So 2/3 times 2. So AI is 4/3. So I have to go from point A, 4/3 of a unit, over in the x direction to get to point I. I can just take the x coordinate of point A, 1, and add 4/3. That is 3/3 plus 4/3 is going to give me 7/3. Okay? And it's going to be the same y coordinate, right? Because it's a horizontal line. So the coordinates of our centroid there, if you have a horizontal or a vertical median, you do have a little shortcut you can use, knowing that the centroid is going to occur 2/3 of the length along that median. If you wanted to, however, we could go ahead and plug this in. Let's take a quick look at how we would do this with an equation. We could take a look at our slope of dB. Okay, it looks like we go down 6 units and over 1. So this is going to be a slope of -6. Okay, so our slope here, m equals -6. And it passes through this point 3, comma 0. Okay, so we could put that into point slope form. Remember, y minus y1 equals m times x minus x1. Okay, let's go ahead and plug in what we know if we call this x1 and y1. Okay, so we get y minus 0 equals -6 times x minus 3. Good. And we can clean this up. We get y equals, let's go ahead and distribute the -6. Y equals -6x plus 18. That essentially converts it into slope-intercept form, which makes sense because our y-intercept is probably somewhere up here around 18. Okay. So now if I wanted to know where these two medians intersect, I could take the equation of this one and set it equal to the equation of that one, right? Essentially, I can go ahead and say if y equals 4, I'm going to plug it in here and say 4 equals -6x plus 18. And I'm going to solve this for x to figure out where they intersect. Okay, I'm going to subtract 18 from both sides. And I get -14 equals -6x. I'll divide both sides by negative 6. And negative 14 divided by negative 6 is 7/3. Excellent. And we already know the y coordinate because that was horizontal. So x equals 7/3, y equals 4. Two different ways to find the centroid. You're going to want to know this way for those instances where you happen to have medians that aren't horizontal or vertical. If you do have medians that are horizontal or vertical, use your shortcut, knowing that the centroid occurs 2/3 of the length from the vertex. Okay, let's try one more of those. Here we have a fan of a local baseball team is designing a triangular sign for the upcoming game. In his design on the coordinate plane, the vertices are located at -3, 2, -1, -2, and -1, 6. Let's call those points A, B, and C. Okay, what are the coordinates of the point where the fan should place the pole under the triangle so that it will balance? Okay, if it's going to balance, we're looking for center of mass, we're looking for centroid. Okay, so we're going to draw the medians in this triangle in order to see where they converge. That'll be our centroid. Let's plot these points. A is at -3, +2. Okay, and we get B is at -1, -2, okay? So B is down here. And C is at -1, +6. So -1, 1, 2, 3, 4, 5, 6. Okay. Okay, and let's just go ahead and connect those lines. And we're going to have a nice triangle here. Some of you are probably already thinking, hey, I'm going to take the shortcut. How do I know I can take the shortcut? One of these sides is vertical, and it'll probably be easy to work with. Let's see if we in fact have an isosceles triangle. That would be what would make it really easy. Let's take this vertical line and find the midpoint of it. We go from y equals -2 to +6. That's up 8 units. So half of that will be 4. I'll go up 1, 2, 3, 4. Here is my midpoint. Let's call it E. This is at -1, 2. Okay. So this actually results in a horizontal median, as you can see. Because we gotta have this vertical side in an isosceles triangle, and that's how it shapes out. Okay. So we could draw another median. We could go maybe up to here, call this point D. Okay. We can use our midpoint formula to figure out what the coordinates of point D are. Okay. If we put D at -3 plus -1, -3 plus -1 over 2, and we put our y coordinate 2 plus 6 over 2, we're going to get point D is at -3 minus 1 is -4 over 2 is -2, and 2 plus 6 is 8 over 2 is 4. Okay, so are we at 2, 4? Excuse me, -2, 4. Yes, that looks right. Okay, so the shortcut here is that we know, if we call this point I, our point of intersection, okay, we know point I is going to occur, so AI will be 2/3 of the length of AE. And we know that AE is how many units long? It looks like it's 2 units long. So deja vu, this is going to be 4/3. So in order to find the x coordinate for I, I've just got to go ahead and add 4/3 to -3. -3 is actually -9/3. So I'm going to end up at -5/3. And of course, my y coordinate will still be the same, be 2. So our intersection I occurs at -5/3, 2. Now, could we do the other method if this had turned out to be a more complicated problem? Sure, we could. We could take a look at this slope. It looks like we've got 1, 2, 3, 4, 5, 6. Our slope is -6. And we know this passes through a point, x1, y1. So let's plug it into our point slope form. So we get y minus -2, which is y plus 2, equals m times x minus x1. X minus -1 is the same as x plus 1. Okay, so we can go ahead and put this into slope-intercept form. Let's distribute that -6. We're going to get y plus 2 equals -6x minus 6. And we'll subtract 2 from both sides. Okay, so the equation for this line is y equals -6x minus 8. Could we find out the value of that where it intersects this line? This line has an equation, y equals 2. Okay, let's set these equal to one another. 2 equals -6x minus 8. And we're going to add 8 to both sides. And we get 10 equals -6x. And I'm going to divide both sides by -6. And we get, here we get x equals -5/3. Okay, confirming what we got when we used our shortcut. Good. Okay, the last of our points of concurrency that we're going to talk about is our orthocenter. Orthocenter is the point that we find when we draw all three altitudes in a triangle. If we draw all three of them, they're going to converge at this orthocenter. And the orthocenter, I'm going to remind you of what we learned about perpendicular bisectors and circumcenter. There were times when the circumcenter would fall outside of the triangle, right? If we had an obtuse triangle and we drew those perpendicular bisectors, right, we would find that the circumcenter would fall outside of the triangle. Could that happen for the orthocenter as well? Turns out it can. If we were to do the same thing, let's take an obtuse triangle. And we're going to draw our altitudes, okay? This one, nice and easy to draw, okay? And this one, I'm going to go ahead and take, we're going not from the midpoint of a side, perpendicular. We're going to go from this vertex at a right angle. That's how we're drawing. I know it looks a little weird. In an obtuse triangle, it looks weird. But that is what that altitude looks like drawn from that point. And likewise, the altitude drawn from this vertex is going to look like this. Okay? Looks a little weird. But that's drawing three altitudes in an obtuse triangle. And yes, in fact, the orthocenter is going to be outside of the triangle. If the triangle is acute, as in our example here, you'll find that the orthocenter is going to be inside the triangle. All right, let's try one example here where we find orthocenter in a triangle. The vertices of triangle ABC are given and plotted here. Can we find the coordinates of the orthocenter? We're going to have to draw altitudes, which means we're going to start, if we pick the altitude from A to BC, we're going to have to go from A until we intersect BC at a right angle. In other words, if we were to draw some point over here, let's call it AE, some point E. AE will be perpendicular to BC. How would I figure out how to plot this line AE so that it's perpendicular to BC? Well, hopefully you remember the work we did in chapter 3, where if we knew the slope of this line, we could find the slope of a perpendicular line by taking the negative reciprocal. The slope of BC is, let's see, we go up 1, 2, 3, 4, 5, 6 over 3, up 6 over 3. That is a slope of 2. Okay, so the slope of a perpendicular line is going to be the negative reciprocal of that. It's going to be -1/2. So let's go ahead and plot that. A slope of -1/2. This guy is going to have a slope of -1/2. Down 1 over 2, down 1 over 2. So I'm going to go through this point right here. Okay, so there is one altitude of the triangle. We'll call this point E here. And it looks like we are at Well, we'd have to calculate it. Graphically, it looks like it's at 2, 0. Now, in order to find the orthocenter, I'm going to have to draw at least one more altitude. So which altitude should we draw here? How about we go from point C to AB? To do that, I'm going to need to know the slope of AB so that I can find the slope of my perpendicular line. Going from A to B, I go up 2 and over 6. You can see my change in Y is 2 units. My change in X is 6 units, up 2 over 6. So 2 over 6 simplifies to 1/3. And that means the slope of my perpendicular line is going to be the negative reciprocal of that. This line is going to have a slope of -3. Okay, so that means down 3 over 1. Okay, or up 3, back 1, up 3, back 1. I'm going to pass through that point right there. And I can connect those points with my straight edge. And you can see here is another altitude that we've drawn. Okay. I'm going to just write on here, I got a slope of -3. Okay. Because how are we going to find the coordinates of this point? Now you might be looking at it and say, Mr. Rogers, I can graphically pick that off. Let's call that orthocenter, and it is at 0, 1. Okay. They won't always be that easy. So how would we find it if this had more challenging coordinates, if we didn't have integer coordinates with nice neat slopes like this? Well, what we would do is find an equation for this line and an equation for this line and set them equal to one another to find those coordinates. Okay, so for this line right here, I could call this x1, y1, and I could plug it into point slope form and say y minus -2, y plus 2 equals m times x minus x1, x minus 1. Okay, and I can convert that to slope-intercept form by distributing the slope -3x plus 3. Okay, and I'll subtract 2 from both sides. So we get this guy is y equals -3x plus 1. Good. Up here, let's do the same thing, except this time we'll call this x1, y1, and we're going to plug it into our point slope form. Y minus y1, y minus 2 equals m times x minus x1. X minus -2 is the same as x plus 2. Good. All right, let's turn it into slope-intercept. We'll distribute that slope. Y minus 2 equals -1/2 x. -1/2 times +2 gives me -1. And then I'll add 2 to both sides to finish it off. Y equals -1/2 x plus 1. Okay, now you can see why it's handy to put these in slope-intercept form, because if you have them both solved for y, then the place where they're going to intersect is the place where they're going to be equal. If these are both solved for y, then let's go ahead and set them equal to one another. -3x plus 1 equals -1/2 x plus 1, and let's solve it for x. I'm going to go ahead and add 1/2 x to both sides. Okay, add 1/2 x. And what I'm going to do here is call this 6/2. So -6/2 x plus 1/2 gives me -5/2 x equals 1. Okay, and I'm going to subtract 1 from both sides, and you might see where this is going. We get -5/2 x equals 0. You can tell there, hopefully, that x equals 0. Okay, so if x equals 0, that's our x-coordinate of our point of intersection, which we got graphically. How do we find our y-coordinate? Let's go ahead and plug it into either one of these equations. Let's plug it in this one because it doesn't have any fractions in it, right? That'll be easier to work with. Y equals -3 times 0 plus 1. And we get y equals -3 times 0 is 0. So y equals 1. Look at that. So we algebraically confirmed what we graphically arrived at. Again, don't forget how to find the slopes of perpendicular lines. Don't forget all those cool things we learned in chapter 3. That is the end of my lesson on medians and altitudes. Let's do a quick review here on what we've learned in the last 2 lessons. Okay. We learned that if we draw perpendicular bisectors in a triangle, if we draw all 3 of them, they converge at this point called the circumcenter. Okay. And the circumcenter is cool because it is equidistant from all of the 3 vertices of the triangle. So if you need to find, this would be handy for designing, say you wanted to make a workstation in the middle of your kitchen, and these are the 3 appliances you use the most. Well, you want to be equidistant from them to minimize the amount of walking you have to do, right? You can also use them for things like substations, locating, how would you locate a power source so that it's equidistant from 3 things that need to be powered, things like that. We also learned about angle bisectors. An angle bisector is drawn from a vertex such that you cut the angle into 2 equal angles. Okay, and if you draw all 3 angle bisectors in a triangle, they're going to converge at this point called the incenter. And the incenter is cool because it is equidistant from the sides of the triangle. Okay, and then we learned today about medians. You draw a median from a vertex to the midpoint of the opposite side of a triangle. If you can tell that this is a median because this is a segment that is drawn to, these hash marks tell us it's the midpoint of the opposite side. If you draw all 3 of them, they converge at a point called the centroid. The centroid is cool because it is the center of mass of the triangle, and the centroid is going to occur 2/3 of the length along the median from the vertex that it's drawn. You can also think of the segments that are created as being in the ratio of 2 to 1. Okay, and then lastly, we learned about altitudes, which we also think of as height, the height of a triangle. If you draw all 3 altitudes in a triangle, they're going to converge at this point called the orthocenter. Okay, so hopefully you guys will be able to remember those. This is one thing that makes triangles super, super cool. They don't have 1 center. They have 4 centers that we've learned about here. Hopefully you guys found that interesting and fun and helpful. And I wish you guys good luck on the homework.